All right, next up we have Team 11. It is my pleasure to introduce Team Fast Track.
Hello, everyone. We are Team Fast Track, and I'm Arina, and I'm here with my teammates Haley and Anj. So, all of you probably have been in the emergency department at least once in your life. And that's because it's really not an uncommon experience. About 1 in 5 Americans visit emergency department every single year. That means that it's a total of 155 million visits annually, and it's roughly 425,000 people in the emergency department every single day. And so when you come to the emergency department, the process is quite slow. The average length of the ED visit is 2 hours, 42 minutes, and in urban hospitals, it can spike to up to 4 to 6 hours. And for conditions such as stroke, sepsis, or heart attack, every single minute of wait can make the difference between recovery and serious harm. So this wait time in triage is not just an inconvenience, it actually is a real biological cost. And so, as you can see from that time breakdown, up to 60% of the ED visit can be spent before a patient even sees the clinician. And for patients with a language barrier, that number can extend to up to 2 or more hours. And so why is that happening? Well, there are many factors we can point to, but from our primary research and clinical interviews, we found that 40% of the delay comes from the documentation burden. And with the development of AI, many companies try to develop some tools that help with documentation or streamline the workflow within the triage, but none of them focus on the pre-arrival intake. And that's the gap our team is trying to address.
So that's exactly what we set out to do with Fast Track, automating triage by capturing patient information before they even step foot in the emergency department, essentially shifting intake from T equals 0 to T minus 0. Now, as Arina eloquently put together, nurses spend a disproportionate amount of time on outdated intake workflows. What we set out to do was replace that with a conversational intelligence system. Now, our system is built around modular architecture. We can think of it as 3 core components that work together in harmony. The first being a patient interface, where all intake conversations happen. Then all intake conversations automatically produce structured summaries that are clinically formatted and ready for nurses to act on. And then finally, all summaries get routed into a nurse dashboard for them to review. But let's look at this in more detail. So the patient starts off with this. They complete a consent form and then move into a guided chat with a conversational intake agent. Under the hood, what happens is we build a canonical turn-by-turn transcript of every part of the conversation, and then on top of that, we layer it with 3 system prompts, almost like a series of them. One to remove misspellings and typos, the second to format that raw text into clean prose, and the third to be able to sort of mimic the style of the user, essentially trying to keep the conversation as natural as possible and less so robotic. And then finally, we also have this concept of memory. At every step of the conversation, we save that state so that tools are able to provide more clarifying questions so that we don't have a monotonic sort of intake conversation happening. What that actually looks like in action is as follows. You can see behind me, we have a patient that says they have a bad headache, that arm is weak and tingly, and they took Advil, but it doesn't help. And as you can tell, that's very messy, but also very clinically rich, and is exactly the type of things we're dealing with and designed around. That raw input gets processed through Gemini Pro as our LLM provider due to its large context window and low latency. We do symptom segmentation and entity extraction, as you can see below, for the chief complaint, onset, and severity. And then we also fine-tune our model on StatProl's medical dictionary so that if a patient was to accidentally mistype the allergy, the tool has the context to be able to recognize what they could have meant. Then with every transcript, we route and pare it down with a user ID and timestamp so that they can save, and we have an auditable record of each and every patient interaction. Those extracted entities that I talked about on the slide before essentially get compiled into this beautiful transcript conversation that a nurse can then see in raw format. But also, they can go ahead into the nurse dashboard where they're able to see the individual parts of the conversation. So the clinical summary, the patient information, and once they're ready after verifying it, reviewing it, and editing it, they're able to go ahead and draft a triage note. The triage note is as similar to the ones we saw directly in the EMR department, and we've tried mapping them with exactly what Epic looks at, making it interoperable with downstream EMRs as well. Now, let's take a step back and actually see the progress we made. So last semester, we were very basic. We were only text, local. It was only specific to my laptop, but we took that a step further. We decided to add voice intake and add support for Spanish to improve patient accessibility at the end of last semester. And then for the remainder of this entire year, what we worked on was adding that back-end architecture so that nurses and patients could communicate on the tool in real time, as well as add language routing for, those edge cases that aren't English or Spanish too.
So now moving on to testing and validation, there really wasn't just one gold standard that we were chasing this entire time, and that's by design. Fast Track is meant to be adaptable to any hospital triage format. So we employed a 3-tier testing framework, testing first information fidelity. So does the system preserve what the patient communicates? Second, platform adaptability. Does the system generalize across formats and domains? And lastly, clinical concordance. Do clinicians find the outputs to be actually actionable? So first, for information fidelity, we performed 2 sets of testing, first being the parameter test and second being the LLM as a judge. And for parameter testing, essentially what we were asking is, does it work? Does Fast Track do what we ask it to do? So for over 180 total runs that we ran with 5 standardized clinical cases as shown here, and with different combinations of language and intake methods, we were able to, at MVP stage, already meet our target performance benchmarks in all the fields that I have on the screen. And for final prototype, even with the additional engineering of prompt and additional features being added, we were able to boost those numbers even higher, surpassing all of our benchmarks. And now moving on to the second part of that testing, LLM as a judge, we really conducted this to take out any sort of bias that we may have as the developers of Fast Track. So we did so by employing LLM as the judge itself to score each of the encounter against a predefined clinical rubric. And we used the same clinical cases and ran a total of 25 scenarios and achieved a very strong set of scores across all different fields shown on the screen. And now moving on to tier 2 of testing, we asked 2 main questions. First, with semantic invariance, we were trying to see if adaptation meant costing us the clinical accuracy. So using same 3 patient transcripts across 4 different output prompt styles, we tested, or we scored for presence of 7 key clinical facts. And as you can see on the screen, we were able to achieve about 75% invariance score, which exceeds the 70% benchmark that is the norm for any sort of pilot clinical LLM systems. And now, moving on to the second question of tier 2 testing, we asked, okay, can it generalize over different domains? So we then created Fast Track OB for pregnancy patients. So it uses the same architecture just for a different domain, and without any extra training, we were able to achieve the scores shown on the screen, which are still very high, very strong, proving the robustness of our system. And lastly, moving on to tier 3 of testing, we had to have that hard conversation with the clinicians, of course, about whether this is actually useful, whether they see themselves using this tool. So we conducted a pilot testing with 3 triage nurses from University of Pennsylvania emergency department nurses, and we were able to receive the scores shown on the screen here. I would like to highlight the clinical accuracy score of 4.1 because the part about triage is, yes, collecting information by hearing from patients, but also another big component is what the nurses can observe from the patients. So for us to be able to achieve the clinical accuracy score of 4.1 without having that component at all was very promising, and that number was also backed up by the actionability score of 4.4, meaning that the nurses didn't feel the need to having to go back and edit or manually type in a bunch of other information after our intake. So with these pilot results, we are projected to achieve around 90% clinical concordance by the end of our proposed full study with bigger cohort of nurses across more ED sites. And thinking beyond senior design to real world deployment, these are some of the limitations that we honestly have been dealing with this entire time. We really constantly had issues with EHR integration and really getting any information out of the hospital, because obviously they want to keep everything private. So to get around those limitations and really push towards deployment, we plan to submit the IRB protocol so we can work within the hospital system instead of just relying on their feedback, and to expand the tier 3 testing with a bigger nurse cohort, as well as involving more emergency departments in the city of Philadelphia. So that is Fast Track, designed and built to revolutionize triage for timely care. And we would like to thank our professors, project manager, Majd, clinical mentors, and our hub nursing team, and all of our participants. Thank you.
Is that working? Okay. So thinking about that clinical context component, will there be a video part of it? Because you can have a patient looking like me and saying my pain is a 10, but I'm not looking like I'm acting like a pain is a 10. And that's also something that triage nurse is taking in. Would there be any component like that?
Yeah, so we're super aware that, one, people can lie about, and people have different sort of pain, thresholds, right? What we're doing is merely replicating the documentation part of what happens in intake. So if I were to go to the intake and say I had the flu, but I was a 10 out of 10, the nurse still has to record that as a source of ground truth in the EMR, and that's the only type of thing we're trying to replicate here.
Okay.
Less so like the clinical decision thing that you just mentioned with having videos or being able to, flag if someone possibly may be skewing their pain thresholds, etc. That could be some sort of downstream thing, but having clinical decision support as a thing to, do for 2 semesters would be way more intensive than being able to just focus on the documentation part.
Yeah. In ERs, there's a huge problem of the amount of patients that are still hanging out in ER beds for sometimes longer than 24 hours, and they can't get them to move up. Just like something to think about for the future, and this would be like a big grand new design of emergency rooms, but if this type of clinical decisions support could help to really, really figure out who actually needs to go in through those doors in the emergency room, who can stay in more like an urgent care right here. And then I can talk to you offline, but there's another app that might be a neat component for you that an emergency room I know is using to help to predict, does this patient need to get admitted or not, so they can fast track that patient who has already gotten in the door to really get to a bed. But it's cool. It's like you're like moving up that timeline for them to evaluate the patient. Yeah. Well done. Very, very well done.
Thank you.
Thank you, Team Fast Track.